We're talking about linear regression here. To start this out, I'm going to show an example here. If you have 2 points, then there's a line that fits that perfectly. Okay, if you only have 2 points. Now notice that we have this correlation coefficient we call R, and a 1 means a perfect fit. It also means a perfect positive fit, which means that the slope of this line is positive, and that there's some positive relationship between these 2 points. Okay, if you were to get R equals -1, now we get R equals negative. The slope's negative. Both of these indicate a perfect fit. Now, whenever we get 3 points or more, which usually we'll have more, then we have to come up with a line of best fit. So I'll show you the line of best fit first. This is the line of what we call the line of best fit. Sometimes we call it the least squares regression line. Now you can see here R is positive because we have a positive relationship, positive slope. And then 0.82 is pretty close to 1, so that indicates a strong positive relationship. Now we only have 3 points, so we have to be a little careful about that. But that's what R tells us. Okay, the closer R is to 1 or -1, the stronger the fit is, and the closer it is to 0, the worse the fit is, or the less relationship there is. Okay, so we call this the line of best fit, but let's talk about what that really means. The difference between the actual point, and actually I'm talking about the y coordinate here, which is 5.05, and the line here looks to be the difference between 5.05 and 1.06. Okay, so that difference is what we call a residual, and the residual here is positive because it's above the line. The difference between this point and the line will be a negative residual, and the difference between this line and this point, though, we have a negative residual here. Now, what this line does basically minimizes the residuals. That's the best fit line. But to be a little careful and clear about this, if you add up these 3 residuals, you always get 0. Notice that 2 of these are negative, and we have a bigger positive residual. And if we add up these 2 negative values and add it to this positive value, we're going to get 0. So that doesn't really help us because it's always 0. But it is good to know. So what we do is just similar to what we did with the standard deviation, is we square these deviations, or these residuals. Okay, and once we square them, they're all positive. Okay, and what this line does, what we call the line of best fit, is the line that minimizes the sum of those squared residuals. Okay, I have to put another point there, but this line minimizes the sum of the squared residuals, and that's why we call it the least squares regression line. So just to show a few things here, just throw some points up there. We can know, what do you think R is going to be? Is it going to be positive or negative? How close of a fit is it going to be? We get 0.67 positive, which we probably knew it was going to be positive. And 0.67, that's how close, that's how strong this fit is. Okay, so now if we get something like that, is that going to be negative or positive? It's going to be negative. And is it going to be closer or stronger than the last fit, or less strong? It's probably going to be stronger. And we get negative 0.96, which is a very strong linear relationship between these two. Now, if we have something like this, I'm just basically looking like a blob, and you can ask yourself, does this variable, or the x variable, have a relationship? Does it impact the y variable? Not very much. Okay, we can see that this is this R value is close to, I'll throw a couple in over here. This R value is close to 0, which means there's not a real strong correlation between what the x variable is and what the y variable is. Okay. For example, if our x variable was height and our y variable was weight, and we got this, we could basically say that, having a higher height doesn't necessarily make you have a higher weight, because what we would expect in that case is to see a positive slope. Higher values of height indicating higher values of weight, which in this case we don't see that. And then there's one other thing I'll show. So first we can take a look at this. Basically the same thing. Okay, this is to show that linear regression and the slope is not resistant. So let me show one other point up here. Now notice the big change in the slope of our line. Also notice the big change in our R value. It was close to 0, now it's 0.9. Now this is saying, yeah, that's a pretty good fit of this line. And that's because we have what we call an influential point up here. So we have to take those into consideration and be a little careful with those. Okay. So going back to what we know about residuals, if we look at this point, let's try to estimate the residual for this point, just looking on the graph. So what we're doing here is we're taking, what is this distance basically? Straight line distance. We know it's going to be positive because it's above the line. So basically what you would do, and I'm not interested in getting it exact here. My tool here is not very accurate, but we're looking at the difference in what the line predicted it to be, which is around 50. Plus what the value actually was, which is around 60. So we're looking at a residual of around positive 10. Okay. Now let's look at another line here, another equation. So this time we have an equation. So if I know that this point right here is the point 45.5. Okay. Now what we're saying is when x is 45, y is 5. Now we notice that as x gets larger here, we don't have any context to this problem. We don't know what we're working with. But as x gets larger, the y values tend to get smaller. And that's indicated by the negative slope, which we would also have a negative r value. This is r squared, which is just the square value of that, which is always positive. And we call that the coefficient of determination. So, but to get this residual, we know that this is going to be a negative value. It's this distance, but it's negative because it's below the line. Now we can get this by saying, well, the residual is equal to the observed minus the expected. Now, sometimes you'll see this as actual minus predicted, which was basically the same thing. What did we actually get? It's what we observed. And what do we expect to get? What did the equation predict? I use observed and expected because that's what the chi-squared uses, and it's in the same order, observed minus expected. So I just use the same language there. So what did we actually observe? We observed 5. When x was 45, we actually observed a y value of 5. Now what do we expect to observe is when you put 45, the x value, into this equation, what do you get out? So I'm not even going to go through that, but just understand that that's the process that we're doing here. The observed was 5, and the expected is when we put 45 into the least squares regression equation. And I'll just call it 83.9. So that's a little bit about residuals and what the least squares regression line is. Okay, so we looked at some values of R. Here's some more. We see R is positive 1, a perfect fit. R is negative 1, a perfect negative fit. Basically, a circular or a blob plot here yields a R equals 0, or R equals close to 0. And then they're saying here R is approximately positive 0.6 and negative 0.6. And it kind of depends on the scale, but you get the idea. This is a positive slope, this is a negative slope. And you can definitely tell that this is a positive, even if you didn't have this line here, you could tell that this was a positive relationship and this is a negative relationship. So that value is 0.6. So before we go on to this next problem, let's look at this. We have an example here. Number of absences versus GPA. So this is just a made up example, but at least now we have some context. Absences versus GPA. So just like you might expect, if I go turn my stat plot on, which it is on, go to Zoom 9, which is what we can always use for our stats. We get that stat plot, that scatter plot. So we understand that that's a negative relationship, and we figured that it would be a negative relationship. So let me do this. I'm going to go to linear regression. I want L1 and L2. My X list is an L1, my Y list is an L2. And I want to store my equation in Y1. So I want to go to variables, Y variables, function, Y1. And now I'm putting this least squares regression line, which is right here, into the equation. Now one thing I'll show here, and you don't have to do this every time. If you go to second 0, that's your catalog. I'll go down to the D's. If you ever, and turn the diagnostics on, make sure it says done. If you ever don't get a R or R squared value, that's why. Just make sure you turn those on. So I'm going to run it again. Notice that our R value is negative 0.98, which is a very strong negative relationship. Okay, R tells us two things: the strength and the direction. Okay, and it's always about its linear relationship. It tells us that it's a negative, strong, linear relationship. So if we have that equation, now let's look at, make sure it's turned on there. We can get that. That's our fit. You can tell that that's a pretty good fit line. So what I'm going to do is trace. I have this point, which looks like one of our larger residuals here. It's 10 absences, GPA of 87. So what I'm going to do is I'm going to do 87 is my actual observed value. I'm doing a residual here. Minus. What I'm going to do is, since I have my equation, I'm using function notation here, which is what I'm saying is I'm going to put 10 absences into my equation. That's just like f of x when you're putting the x value into the function. Okay. So my equation's in y1. I'm putting 10 into that, and I'm subtracting it from my actual value, what I actually observed, and I'm going to get my difference. That's my residual. Okay. And actually, as soon as you run, I wanted to show the concept there, but as soon as you run a regression line, your calculator, if you go to second stat, go to your lists, it actually has a residuals list. And you can go there, and somewhere down here we should see 1.726. And there it is. Okay, that gives us our list of residuals. Now one thing I'll do here, if I add, I go to second list, math. Let me say add. Sum. My previous answer, which is the residuals. We said we were going to get 0, and that's basically what the calculator is telling us, to 12 decimal places. 0.000, that's 11 times, and then finally you get a 7. So if you do add your residuals, you do get exactly 0. Just got a little calculator error there. So the next thing we're going to do is we're going to be interested in testing to see whether the true slope between two variables is 0 or if it's not 0. If the true slope between two variables is 0, then what we're saying is that they're independent of each other. There's no useful linear relationship between those two variables. And if the slope is not equal to 0, then there is some type of useful linear relationship. Okay, so let's show this first. Okay, if the slope is 0, which the slope is 0 here, what we're saying is even when x got larger, y didn't change. So y is not dependent on x. So that's what we're testing here. So first of all, let's just understand what we're doing here. We have some big population. I didn't give this any context. Well, we have this big population. Well, let's go back to what we just did with absences and GPA. Let's just say this is our entire Savannah Arts Academy population. Everybody has their number of absences, and they have their Y value is their GPA. Well, if I can't look at everybody, which is a lot of times what we have to do in statistics, I'm going to choose a sample. So I'm going to choose this sample, 1, 2, 3, 4. Okay, and this is my line of best fit. Of those 4 values, that's my line of best fit. Now that's not my true line of best fit. You can see that the true line would probably be somewhere in here, slid down a little bit and probably a little less steep. Okay, but based on our sample, that's what we get. So what we're saying is, if the true slope between these two variables was 0, how likely would it be to choose 4 values and get this a line this steep, positive or negative slope? Okay, so what we're going to do is we're going to read some computer outputs. Before we do that, so basically this is saying this is the population with a bunch of different points, and each one of these red lines represents a sample line. In other words, the black line is probably the true regression line between this population. But if we choose just some certain amount of points, we're going to get a bunch of these red lines. Okay. Notice that we never really have a negative slope, but it is possible to have a data that's truly positively related, but choose an unlucky sample and get the slope to be negative. So notice that what this distribution is the slopes of each line. The most common slope is about 1, or I guess 1.5, 1 to 1.5. That's the most common slope. So the most common slope of these red lines is that. Notice that every now and then, well, I guess, no, sometimes we do have a negative slope, because this slope's between -1 and 1, and not seeing it up here, but that's what this is saying. This is a histogram of the slope. How many of those slopes? And this is a histogram of the y-intercepts. Now we're not as concerned about the y-intercepts. We're more concerned about the slopes here. But this is how the y-intercept. Notice the most common y-intercept is about 1, and that's why we're seeing a big, large value there. Okay. So let's go back to how we read these computer outputs. This is one sample line, and we're looking at the height of a tree versus the volume of a tree. Height is the x variable, or the independent variable, and volume is the dependent variable. Now this is the slope of our sample line, 1.54. Notice that you see this here, 1.54 times x, which is the height, in our equation, plus my y-intercept. So this is my y-intercept here. Okay. This value represents the standard deviation of the slopes. In other words, if I chose another sample, I'd get a different slope. If I chose another sample, I'd get a different slope. But those slopes vary. A typical difference on those slopes is this. This is the standard deviation of the slopes. Okay, so that's going to be able to create and we don't use these values as much because, again, we're not as concerned about the y-intercept, more about the slope. But this is the t-value that we use if we test to see if the slope is equal to 0. And we'll get into this a little bit more in class, but we get a t-value of 4.02 and a p-value. This is testing exactly what we showed earlier. Is the slope equal to 0 versus the slope not equal to 0? So we have a low p-value, which gives us evidence to reject HO, or it gives us evidence that the slope is not equal to 0. And remember, if the slope is not equal to 0, we're saying there is some type of relationship between height and volume of a tree, and that makes sense in this example. Okay, the taller a tree is, the more volume you're going to have. Okay. This number, S, 13.4, represents the standard deviation of the residuals, the sample standard deviation of the residuals. In other words, for our equation, our sample that we took, if we took all of our residuals, we took the standard deviation of those residuals, that's the number we get. Okay, so that's an estimate of the true value of the standard deviation of all of those residuals if you look at the population. Okay. Now, here they didn't give us an R value, but we could take the square root of R squared. We don't want to work with R squared adjusted. That's for multiple regression. So if you take the square root of 35.8 or the square root of 0.358, you get your R value. And since this value is always going to be positive, we have to remember, okay, is R going to be positive or negative here? Well, if the slope is positive, then the R value is going to be positive because they're both positively related. So take the square root of that, and it's the positive value, that's our R value. And that would give you your correlation coefficient. Okay, and the rest of these values we don't need. This is analysis of variance. That is ANOVA, which is the one thing in AP statistics that we don't cover. Okay, so we'll look at one more and then that'll be it. This is we're trying to predict a math score versus, or we're trying to use an essay score to predict how someone would do on a math exam. Okay, so when we looked at all of our data, we got this is our slope, goes right there. This is our y-intercept, goes right there. This value represents the standard deviation of the slopes. Okay, or standard deviation of the slope. In other words, if we took another sample, we're going to get another slope, and how much those slopes vary is this much. That's a typical difference on those slopes. This time we get a t-value, again testing whether the slope is 0 versus whether the slope is not equal to 0. We get a t-value of 2.08, which gives us a p-value of 0.072, which is higher than alpha, which are the most common alpha of 0.05, which would lead us to fail to reject. So this does not give us any evidence that there's a linear relationship between how someone scores on an essay versus how someone scores on a math exam. Okay, at least not at the 0.05 level. And again, this is the standard deviation of the residuals. And if we took the square root of 0.35, we would get our R value. Again, the slope is positive here, so our R value is going to be positive here. So we would have all of those values.